QCQ, this is Kilo Quebec 4 Victor X-ray Oscar.
Hi everyone, welcome back to the channel. My name is Shri, I'm an RF engineer and a licensed ham radio operator. On this channel, I'm sharing my passion for practical RF circuit design and antenna design. So if you're new here, please like, share and subscribe. So in the last video, we have taken a look at each of these pin operations and what they are meant for. We will have to dive a little bit deeper to fully understand the capabilities of this IC. Before we dive deep into the functioning of each of these pins, let's just take a look at the packaging of this IC. LFCSP stands for lead free chip scale packaging. So if we look into this IC from the top view here, what we will see is the die connected to each of these pins on the packaging with gold bond wires. But if we cut it and look at the cross-sectional view, what we will see is a base with copper plated pads that have solder on the bottom to facilitate PCB mounting. But the interesting part is on the inside. There is a die mount on top of which the actual die sits on. And then this whole thing is covered with epoxy. And each of these pins is connected with gold bond wire. And the complete die is covered in molding compound. So this bottom pad, exposed pad, is connected to the PCB and helps dissipating the heat through the multi-layers PCB. Let's talk about the first 4 pins: the clock, data, load enable, and chip enable pins. So pin 1 is serial clock input. From this timing diagram, we can understand that the data that is given through this chip will be moved into this 32-bit shift register on the rising edge of this clock. And then the pin 2 is the data, which is loaded MSB first, followed by 3 control bits. So the control bits define which register the data is moved into. And then we have the load enable. When load enable becomes high, that is when the data will move from the 32-bit shift register to one of the 6 registers, R0 to R5. How to pick that will be defined by C3, C2, and C1. And then the last one is CE, the chip enable. The chip enable is basically a power down and a power on switch for this chip. So for applications where it is required to have the ability to power this ADF4351 down, we will connect this to the microcontroller and it uses the CMOS logic. Or you can also connect it to the power pin on VDD, and then the chip will always be on. So pin 5 is the fast lock switch. It can be enabled or disabled based on the application. We can take a deeper look at this while programming the ADF4351 with an STM32 microcontroller. VP is the power supply for the charge pump. This should be tied to the VDD of the chip. CP out is the current that will be connected to the VTune pin via the loop filter. So we will have the output of the charge pump connected through a loop filter and then to the VCO, the tune part of the VCO. And then the next one is pin 8, which is the CP ground, which is the return path for the charge pump current. 9 is an analog ground. We will have to ground that. 10 is the analog supply, the VDD, which is the 3.3 volts. And then you have the VCO analog ground on pin number 11. Then comes the 2 RF outputs, RFA and RFB. So pin A is the preliminary and pin B is auxiliary. And each A and B are divided into A plus and A minus, the differential signal, which is basically 180 degrees inverse of the A plus. So these pins can be enabled or disabled either by terminating it physically on the board with a 50 ohm resistor. So if we are not using the auxiliary, we just terminate that with a 50 ohm, or you can also disable them in the software. And similarly, if you are using a single-ended, the RF output A should be matched to the A plus, A minus should be matched to the A plus. The input matching allows for a little bit more output power than what is shown in the datasheet. We can take a look at how to tune or how to match the outputs for single-ended applications. And then comes the supply for the VCO. In this case, it is 3 different VCOs with overlapping bands. We'll take a deeper look at that. Pin 17 is also a supply for the VCO. So these two should be tied together. Pin 18 is the analog ground for the VCO. Pin 19 is the internal temperature compensation, and this should have a decoupling capacitor very close to the chip. Pin number 20 is the V-tune, where output of the loop filter is connected as the input here. And then we have another 21, which is the analog ground for the VCO. And then we have 22. The R set is the resistor that we have to define for the amount of charge current we need out of the charge pump. So I will be defined by this resistor R set. And the nominal voltage at pin 22 is 0.55 volts. There is an equation in the datasheet that will help identify the resistance value needed for the amount of current you want for the application. And the datasheet has a table on how the current varies with the resistance value. So pin 23 VCOM is the internal compensation node. It is biased at half the tuning range, and we have to place decoupling capacitors just like the pin 19 temperature. And then Vref is the reference voltage. And this should also have decoupling capacitors very close to the chip. Moving on, we'll have pin 25, which is lock detect. This is both analog and digital lock detect. This can be used as a sync out. So when the PLL is locked, it goes high. So this can be used as an interrupt to another microcontroller to start its operations, or if you are using this as a signal generator, which can be used as a trigger to do different measurements. Pin 26 is an RF power down or an RF mute. This can be used to mute the RF output. And it also has the feature to mute the output of the RF till the PLL has locked. And then you have the digital ground for both 27 and 28. 29 is the reference in. This is where we will have the crystal oscillator connected. And then 30 is the mux out. The multiplexer has the option to read the lock detect value, the N divider, the integer N divider value, or the R counter value. All of these are internal to the chip. So the ability to read the lock detect, integer N divider, or the R bit counter values through the microcontroller helps define what is the actual frequency output being put. It can work as a feedback to create a closed loop signal generator. Pin 31 is the digital modulator ground, and pin 32 is the supply for the same digital modulator. We should have decoupling capacitors very close to the chip for this pin as well. As you can see, there's multiple pins that require a decoupling capacitor very close to the chip. It is important to identify the values of these decoupling capacitors and the packaging size, either a 0402 or a 0603, since the real estate closer to these pins is very small. Now that we have looked into the basic pinout functions of ADF4351, we can proceed to understand the sigma delta modulator operations and how to load the register values in hexadecimal from R0 to R5 in the right order to get the desired output and the resolution of the channel. But before we go into that, let's take a look at how the RF output is generated. From the datasheet, we get these two equations. The RF output is dependent on the integer divider, which is a 16-bit value that goes from 23 to 65,535. 0 to 22 are reserved for internal operation. The fractional and modulus values basically act as the numerator and the denominator to set the fractional divider. Both of these are 12-bit, going from 0 to 4095. FPFD, which is the phase frequency detector frequency, this frequency is given by equation 2. And then finally, we have the RF divider, which is the integer divider at the output of the VCO, which goes as 1, 2, 4, 8, 16, 32, and 64. The FPFD is an input signal to the phase detector that is compared against the reference input from the crystal oscillator. So here we have the input from the crystal oscillator multiplied to this value. And this is defined by the reference doubler, which is D. R is a 10-bit counter that goes from 0 to 1023. And T is the reference divider of the reference input, and which is divided by 2. So the reference doubler and reference divider are essentially a switch that can be either 0 or 1. So in a normal operation mode, these are both set to 0, and 10-bit counter value can be adjusted in the register 0. All right. In the next video, we will take a look at how we can calculate the integer, fractional, and modulus values for a given reference input crystal oscillator and get the required output frequency. We will follow that up by building a signal generator for MR application and also including sweep options for certain bandwidth. If you come to enjoy this content, please like, share, and subscribe. Thank you.